Hi everyone, this is the second set of lectures and this is a recorded video. In the previous lectures, we have learned that for sinusoidal current, the root mean square current is given simply by the maximum current divided by square root 2, and that the mean power is the maximum power divided by 2. You see here there's a missing column. There will be something else that will be filling up after the set of videos today. So back to the learning outcomes, we will be learning in this video an understanding of a transformer and how does this equation come about. And in the next video, we'll talk about how a single diode is used for half-wave rectification of alternating current. So transformers. This is a transformer in real life, but from the exterior, you really don't know what is happening inside. So that is why we have this kind of pictures, a schematic to show you what it really happens. In this video, I'll guide you through how a transformer works. So why do we actually need to use transformers? Transformers allow, essentially, to let us step up and down current. But we want to step up and down the current to actually to step up and down the voltage. And we want to step up and down the voltage simply because we want to reduce the current such that we can reduce the energy loss. So the main aim, or the main goal at the end, is to reduce energy loss. So let's look at it, the schematic with the picture. After your power plant has produced the power, producing a alternating voltage, your transmission substation will actually step up the voltage to a higher voltage to transmit along these high voltage transmission lines. The high voltage transmission lines are denoted by these wires in pink. Thereafter, when the current transmits past the substation through the power poles and the cables, we arrive at the transformer drum, which happens right before the end user, to step the voltage back down to a manageable 240 volts root mean square. A transformer consists of two coils, schematically. This is how you draw it. Right? This is what it looks like. This is what it will draw in a circuit symbol. But in reality, right, the two coils are actually not apart from each other. There's a reason for this that we actually call it one above the other, which I'll explain later. Your handphone charger essentially has a transformer in it. Why? Because the voltage that we draw from the mains is actually at 240 volts, but we need to actually convert it to step it down to a lower voltage of 5 volts and then after convert it to a DC. In the other video, a video following this, I'll actually talk about how you convert an AC to a DC. So I've told you why we need to use a transformer, why we need to learn about transformers, simply because we need to save energy. We need to step it up to save energy by limiting power loss. So let me prove it to you with numbers. So a nuclear power station, right, is producing 2 megawatts of electrical power and is transmitting it through cables which have the result of 5 ohms. If you look at the schematic, it looks like this. Power station, across the ends of the power station, the potential difference is 500 kilovolts. We have wires, the total resistance of 5 ohms, and this is the end user. So to find the power loss in the cable, we have to first find the current transmitted in the cables. Since we know that the power of the power station is 2 megawatts, the potential difference across it is 500 kilovolts. The current is essentially 4 amperes. Since the current is 4 amperes and the resistance of the wire itself is 5, using power loss equals to I square R, we get 80 watts. Note here that I did not use P equals to VI to find the power loss in the cables. Many students use P equals to VI or P equals to V squared over R and wrongly substitute the value of V here into the equation. They either get back the original power that was supplied or a larger power. This does not make sense because majority of the power should be consumed at the end user and not in the power cables. Next, we are asked to calculate the voltage drop across the cables. Since the current across is 4 amperes and the resistance is 5 ohms, we have a voltage drop of 20 volts. Now, note that this V, the voltage across the cable, is not the same as V here, which is the voltage produced in the power station. If you want to use power loss in the cable, so some students ask me, right, Mr. Ho, can I use power loss in the cables using VI or V squared over R? Actually, you can. However, you must be very careful that the V that you're using is actually the potential drop across the cables rather than the potential difference across the cables in the power station. Alright, so do note that this V here is the V across the cable, not the V across the power station. Okay, they will lead you to vastly different results. Part C, you're asked to find the voltage, output voltage at the destination load. Since you have a voltage potential difference of 500 kilovolts, 20 volts is consumed, what you are left with is 499,980 volts. Next, let me convince you once and for all that stepping up the current is useful if your input voltage is actually lower at 5 kilovolts. The current that will be transmitted through these wires will actually be 400 amperes. Using the same method of calculation, the power loss in the cable would then be I squared R, which would then be 400 squared times 5, which would be 800 kilowatts. Note that 800 kilowatts is a much larger number than 80 watts. This shows that by stepping up your voltage, you actually have less power loss. The next example, in the previous example, we used numbers to show that the power loss is less when you step up the voltage. Let's see if we can prove that, not on a case-by-case basis, but prove it generally. So at any instance, for any power supply, at a potential difference in the power station, you would have a current. The current will be given by the power of the power station and the potential difference across the wires in the power station. The power loss in the cables then will be the current transmitted and the resistance of the wires. Hence, the power loss is simply P over V here squared times R. Since the power of the power station squared is constant, the resistance of the wire is constant, we can say that power loss is inversely proportional to the square of the potential difference across the generator. Okay, this shows that power is inversely proportional to the square of the input voltage. Next, let's talk about the functioning of a transformer. In the notes, I've given you a paragraph of text, but let me now delineate it and give you the reasons chronologically, the functioning of it chronologically. First, you must have an alternating voltage supplied to the primary coil. This is the primary coil, V being the voltage and P meaning primary. If you apply an alternating voltage to the primary coil, you will have an alternating current. If you look at this coil, if the voltage is going clockwise, a current is going clockwise, you use your right hand grip rule over here, you will see that the B field is pointing up on this side. If now the current is traveling in the opposite direction, that means in the anti-clockwise manner, you can see using your right hand grip rule, right, or the current traveling to the left on these wires, that the B field actually points downwards. This means that as the current alternates between up and down, clockwise and anti-clockwise, we have the B field alternating between up and down on the primary side. Hence, with an alternating voltage, you have an alternating magnetic flux inside the iron coil. The alternating magnetic flux in the primary coil causes an alternating magnetic flux in the secondary coil. If it points up here, it will travel this way, up to the right and down on the secondary side. If it were to traveling down on the primary side, it will point up on the secondary side. So our alternating magnetic flux on the primary coil will have an alternating magnetic flux in the secondary coil. We have learned from EMI, electromagnetic induction, that the alternating voltage, right, alternating magnetic flux will induce an alternating voltage in the secondary coil. Okay, this is from the Faraday's law and your Lenz's law. If the resistor is connected across the terminals of the secondary coil, induced current will flow, and thus we have voltage and current on the secondary side. This means that we have power transmitted. So the power given in the primary coil is VPIP. The power received on the secondary coil will be VSIS. Okay, and depending on the coils that we have, the voltage can be changed from the initial voltage Vp to the final voltage Vs. Now let's talk about the workings of the transformer in a little bit more detail. This is the overall idea, but to look at this in whole is a little bit difficult, so let me split it in two parts. Let's first look at the primary coil. Previously, we know that if we apply a voltage Vp in the primary side, we will have a current. That's true. However, let's look at it in a little bit more detail. For the primary circuit, if you apply a potential difference Vp here, a current will flow, and since the current flows and this wire has a resistance, there will be some potential difference consumed, Ip times R of the wires on the primary circuit. This is the potential consumed, this is the potential difference applied, this is the potential difference consumed in the wires, and across the coils you will have actually an EMF, an electromagnetic force. We have learned that electromagnetic force, right, is actually given by electromagnetic flux linkage. Affects the rate of change of magnetic flux linkage. Since the EMF is given by rate of change of magnetic flux linkage, and magnetic flux linkage is essentially NBA, and since the number of coils N does not change, we can bring that out of the equation such that EMF now becomes N, the number of coils, and the rate of change of magnetic flux. If we now then assume the resistance of the wires to be small, we can then say that the applied potential difference is very much close to the EMF being given, where the EMF in the primary coil is given by the number of coils times the rate of change of magnetic flux. So let this be equation number 1 for the coil on the left hand side. For the coil on the right hand side, we repeat the same picture. The EMF produced will allow a consumption of potential difference on the secondary side, and there will be some losses due to the resistance in the wire given by I times R, the resistance of these wires. Right, so I say again, so E equals to V plus IR. But we see, applying the same idea to simplify, if we say the resistance in these coils are small, and essentially it should be, we know that the potential difference across the secondary load will be more or less equals to the EMF given in the coil. And the EMF in the coil is simply the number of coils multiplied by the rate of change of magnetic flux. So if you combine these two equations from the left side, the primary coil, and the secondary coil side of the transformer, we essentially have this. And if we assume that the rate of change of magnetic flux is actually constant, assuming no loss of magnetic flux, we can actually arrive at this formula. And we see that the turns ratio, which is very strictly said as the number of coils on the secondary side over the number of coils on the primary side, is given and is related to the potentials in this manner, which is to say the potential in the secondary side is high compared to the primary side when there are more coils in the secondary side compared to the primary side. Okay, this is what you have learned in primary school, in secondary school, and you notice that in JC we tend to prove some of the things that you have learned and do not just take them at face value. So this is also what you have learned. This is a reminder. If your number of coils in the secondary side is more than the number of coils in the primary side, essentially the voltage output will be more than the voltage of the primary coil. We call this a step-up transformer. Conversely, if it is the other way, we call it a step-down transformer. Next, if the transformer is ideal, there'll be no power loss, right? There'll be no power loss, and the input power will be equals to the output power, which is to say P on the primary circuit equals to P in the secondary circuit. Since power is equal to VI, we can then say that VP equals IP and Vs equals to Is. If we rearrange, we have Vs over Vp equals to Ip over Is. That is to say the ratio of the voltage is inversely proportional to the ratio of the current. Right? So you have Vs over Vp equals to Ip over Is. If we combine both, then we see that we can actually write out this equation. Right? So let's look at one example. Once again, from the videos we have seen before, 24 watts here refers to the mean current consumed by the lamps. 12 volts means 12 volts VRMS, root mean square voltage. The mains has 240 volts, which means that yes, 240 volts root mean square. Okay, these are points that are not mentioned in the question, but it's expected that you should know it. So questions ask for what is the turns ratio of the transformer. So turns ratio is essentially the number of coils on the secondary side versus the number of coils on the primary side. Since we have the voltage on the secondary side and the voltage on the primary side, we can simply sub in the values and we get turns ratio to be 1:20. What would be the current drawn from the mains if the transformer is 100% efficient? So what is the current drawn on the primary side? So what is IP? What is IP? That's essentially what this question is asking for. Right, so the current drawn from the mains is 100%, which means the powers are equal. So let's start by finding the current going through each lamp. If the power of each lamp is 24 watts, and the potential difference across each lamp is 12, then we can say that the current, or rather the root mean square current more specifically, is actually 2 amperes. If there are then 10 lamps in parallel, the total current, root mean square, will be 20 amperes. So if the transformer is 100% efficient, the power in the input at the primary coil will be power output at the secondary coil. Applying this equation and substituting the appropriate numbers, we find that the current in the primary coil is actually just 1 amperes. Now, if we use our own experience, I think many of us have handphone chargers and laptop chargers. If you touch the power brick of your laptop or the adapter of your handphone, you'll find that it's actually pretty warm, right? So if it's warm, it means that it's producing heat. If it's producing heat, that means that there's some kind of energy loss, and hence there must be some form of power loss. In this section, we will talk about what are the losses in a transformer. But before that, we need to talk about the efficiency of transformer. We want, of course, the efficiency of transformer to be as high as possible, the maximum value being 100%. And the efficiency of transformer is given by the power output in the secondary coil over the power output in the primary coil. So if energy can be lost in the following ways: resistive heating in the coils due to eddy currents, hysteresis, and leakage of magnetic flux. The first point is pretty obvious. In your coils, it's a wire. Wires in real life have resistance. So using I squared R, there's certain power loss, there'll be certain heat loss. In eddy currents, so first, what are eddy currents? Well, if you have a current coming into the primary coil, and if you follow current and use your right hand grip rule, you know that there's a certain magnetic field being produced pointing to the top of the pitch, right? Here. So we are using a certain instance of time. At this moment of time, if the soft iron core sees the B field increasing upwards, it will want to counter this increase of B field. Using Lenz's law, right? Using Lenz's law, we see that the current being produced must go in a clockwise manner to counter the B field being produced by the coil. This current is called an eddy current. This current, being in metal, being in a soft iron ore that has resistance, will then produce a power loss, right? Using P equals to I squared R. So to limit this current, we actually can laminate the transformer into many parts separated by insulation to minimize the flow of eddy currents. So if you minimize the flow of eddy currents, you will minimize the power loss. Next, hysteresis. All soft iron ore will have a little bit of magnetization retained even when the current is switched off. When an opposite field is applied, some energy will be needed to change the magnetic domains of the coil to reverse in direction, right? And as we know, the current in the mains has a frequency of around 50 Hz, which means that the direction of field is changing about 50 times a second. All right, so to change the directions, we actually require a little bit of energy. And since energy is lost, there'll be some power loss in the transformer due to the hysteresis. This is also a reason why we do not use a hard iron core and we only use a soft iron core, right? Because hard materials retain their magnetization very strongly even after the field is removed. Lastly, another form of leakage, another form of loss of energy comes in the form of magnetic flux leakage. This is also the reason why, as I mentioned before, that the wires are wound over each other in this manner, so as to limit the current, so as to limit the flux flowing or leaking out of the coils. When the coils are wound over one another, the leakage of magnetic flux is minimized. Okay. Right, we have come to the end of this lesson. In the next video, I'll talk about the half-wave rectifying circuit and how a diode can be used in a circuit to rectify a circuit.